Modern language models like GPT-3 operate on a scale that is difficult to process. We are looking at architectures containing 175 billion independent parameters. When you want to teach a model of this size a specific new task, the standard approach is to update all of those weights. But doing so creates an immediate massive bottleneck in memory. Fine-tuning GPT-3 requires 1.2 terabytes of VRAM. This footprint includes the baseline weights, the computed gradients, and the atom optimizer states for every parameter in the model. That hardware requirement pushes iterative testing and rapid task switching out of reach for anyone without access to a massive supercomputing cluster. Treating a model's entire parameter space as fully independent variables that must all be tuned simultaneously for every minor adaptation is practically unsustainable. In 2021, a team of researchers led by Edward Hu proposed a mathematical bypass to this bottleneck called low-rank adaptation, or LoRA. Their approach relies on a specific property of neural networks. They hypothesize that the weight updates necessary to learn a downstream task possess a strictly low intrinsic dimension. By exploiting this low dimensionality, LoRA shrinks the trainable parameter count on GPT-3 from 175.2 billion down to 4.7 million. That is a 37,000 times reduction, cutting VRAM usage to 350 gigabytes. The mechanics of how this works start with a hard lock on the original model. The massive pre-trained weights, known as W0, are completely frozen. The system stops computing gradients for them entirely. By locking the core network and heavily constraining the space of trainable parameters, this method decouples the process of task adaptation from the brute force scale of the underlying model. Standard dense layers in a neural network process data through forward pass matrix multiplications, typically expressed as h equals w times x. LoRA modifies this equation. The output is determined by the frozen pre-trained weights, plus a delta weight update, giving us h equals w0x plus delta wx. The massive w0 matrix is locked in memory. Instead of calculating a massive update, LoRA uses two smaller matrices. Matrix A compresses the input dimension to a tiny rank R. Matrix B projects it back out, forming a weight update matching the original layer. The efficiency here relies on the rule that the chosen rank R must be drastically smaller than the layer's original dimensions D and K. Before this matrix product is added to the network, it is multiplied by a scaling factor of alpha divided by R. The alpha variable acts as a stabilizer for the magnitude of the weight updates. This structural feature allows engineers to adjust the rank without constantly retuning their learning rates. The result is a mathematically rigorous decomposition. It isolates the learning process into a constrained subspace, leaving the foundational knowledge of the language model untouched. Injecting randomized matrices into a balanced 175 billion parameter model carries significant risk. A chaotic initial update could corrupt the model's outputs. To prevent this, the initial weight update, the delta W, must equal 0 before the first training step begins. LoRA accomplishes this requirement through a specific initialization constraint applied to matrices A and B. Matrix A is initialized using a normal distribution, providing the statistical variance required to begin learning. Matrix B is initialized to mathematical 0. Upon the first forward pass, multiplying this active noise matrix by a matrix of zeros yields a product of purely 0. Because the delta remains at 0, the modified model behaves exactly like the base pre-trained model on its very first pass. This zero initialization strategy ensures safe, monotonic learning. It prevents the optimizer from inducing catastrophic forgetting or destabilizing the pre-trained weights during the early epochs of adaptation. A common engineering assumption is that teaching an LLM a complex new task requires a high rank R to provide a large enough parameter space for learning. To test this, the authors conducted rank ablation studies, observing how the model performed on datasets like WikiSQL when varying the rank. This chart shows the benchmark performance. When restricting the rank to R equals 1, the model still achieved 73.4%. When they increased the rank to 64, the performance flatlined, stopping at 73.5%. Increasing the parameter space by 64 times yielded no measurable improvement. The data required to adapt to a new task is extraordinarily concentrated. If raw parameter volume does not drive performance, the question shifts to where within the transformer block those limited parameters should be allocated. One strategy concentrates a larger parameter budget, like R equals 8, entirely on a single target, like the query matrix. The contrasting strategy divides a smaller budget, like R equals 2, spreading those updates across the query, key, value, and output matrices simultaneously. The empirical results are definitive. Distributing a smaller rank across multiple attention matrices consistently outperforms concentrating a larger rank on just one. Effective fine-tuning relies on ensuring that a highly efficient low-rank update has spatial access to multiple facets of the attention mechanism at once. After the low-rank matrices converge during training, the focus shifts to deployment and live inference. Traditional methods, like standard adapter layers, share a distinct mechanical flaw. They force the incoming data through additional sequential computational steps, creating latency. LoRA bypasses this sequential bottleneck by leveraging basic linear algebra. Since the trained matrices have converged, we use the formula W equals W0 plus the scaled product of BA. This BA product shares the exact dimensional shape as the original W0 matrix. They add directly together to form a single unified weight matrix. When deployed, the combined architecture is identical in shape and depth to the original base model. Because no new layers were added to the pipeline, this architecture introduces 0 milliseconds of additional latency during token generation. System architectures can maintain the massive W0 base in memory and swap specialized BA matrices for different tasks on the fly, enabling dynamic multitask processing. Evaluating these mechanics against rigorous benchmarks proves the viability of the LoRA approach on massive scales like GPT-3 175B. Looking at this benchmark data, when tested on datasets like multi-NLI, LoRA achieved an accuracy of 91.7%, outperforming the full fine-tuning baseline of 89.5%. The authors suggest that forcing weight updates through a tightly constrained low-rank bottleneck acts as a form of regularization. It prevents the massive model from overfitting to the specific downstream task. The method produces superior natural language adaptation while updating only 0.001% of the model's total parameters. By mathematically proving the low intrinsic dimension of learning, LoRA successfully decoupled model adaptation from brute force compute. It moved cutting-edge model tuning away from the supercomputer cluster and into the hands of the individual engineer.